Hi everyone. In this video, I'd like to explain how the Math Inspector source code works. The main topic I want to discuss is how Math Inspector is able to create a visual representation of the memory of the running program. I think a video like this is going to be really useful for anyone who'd like to contribute to the Math Inspector repository on GitHub, or maybe just if you're interested in learning about how Math Inspector works. So the first thing you'll notice here is that I have the main file open, and that's the entry point for the rest of the source code. The reason that it's in main is, so here's the root directory of the project, and then this is the Math Inspector directory. So it's called main because when you're on the command line, you can type Python Math Inspector, and then it's going to launch the app. So let's just come into this file and go through it line by line and talk about what's going on. Right here, we are importing tkinter as tk. Now, tkinter is a framework for creating an app on the computer. If you come from a web development background, maybe a good way to think about it is that tkinter provides things sort of like HTML and CSS, and then Python is sort of like the JavaScript. It's not exactly like that, but that's a good way to think about it. Here we have TTK and themed TK, and that's just going to make the style of the app look nicer. And then here we have the core Math Inspector components. The way that it works is that we have this class named app, and then it's going to run the main loop. This is a tkinter function. Okay, so let's take a look at the init method of this class. What we're doing here is just setting up the style. That's all. So then we have these paned windows. What's a paned window? I'll show you right now. So we're going to launch the app. And now this is a paned window, and this is a paned window. Okay? So coming back into the code here, we see that it's going to create this thing called the side view, which is a notebook. A notebook is something that's in tkinter. And this is a notebook. You see it has these tabs, and you can switch between the tabs. So the first thing I want to look at is actually the object area. When you write x equals 1 in Math Inspector, it's going to create this item x, which we can drag around, and then it's going to appear in the object view. Let's just skip to this line. You see how it says objects, self.objects equals object tree? This business here, that's a tree. So if we had another variable, let's just say y equals 2. Now you can see that we have this sort of directory structure here, and if we were to import numpy as np, then in the modules view, this is a tree. Everything that we're seeing here, the self.node, self.console, etc., we can access from Math Inspector by typing app. So for example, we're going to be looking at this app.objects. You can see it's called object tree. And in order to look at all of the objects, we're going to type app.objects.store, and it's going to give us an ordered dictionary. And so this app.objects is what's called a vdict, which stands for virtual dictionary. That's sort of at the heart of what's going on in Math Inspector, and it's used all throughout the entire code base. Let's take a look at the objects file. This class object tree is extending two classes, vdict and treeView. So let's take a look at vdict. The main thing about a vdict is that it's got callbacks for getting and setting and deleting items. And that's sort of the secret sauce that makes everything work. By the way, you see here self.store is an ordered dictionary. So what happens is it's just a regular dictionary, and a good way to start learning about this is we can just type right here from util import vdict. So what's going on is that you can import right here from the interpreter anything in Math Inspector. And so here we have the util package, and it's got a vdict. So let's instantiate a new vdict. Let's say that A is equal to vdict. And the way it's going to work is we're going to say set item equals, and we're going to make a lambda function. And it's going to have key value. Let's just print the key, okay? And now what we're going to do is we're going to set A of, say, x equal to 1. And you can see here it actually printed our key for us. That's what I mean when I say that there's callbacks. Okay, so we've discussed that app.objects is actually a vdict. So if I were to say set it to 11, you can see it got updated here to 11. In fact, what's going on is if I type x equals 11, that's exactly the same as typing this command. App.objects represents the memory of the program and the tree view. The way that Python manages the memory of the program is with the local and global namespaces. In order to show everything that's in the local namespace, we call the built-in locals function like that. And we can see that it's got this thing app, and it's got another one plot. And then if you type globals, it's going to show you the objects in the global namespace. The locals and the globals are the same. The reason I did that was because I was following the official patterns in the code module for how to create a new Python interpreter. The way Math Inspector was built is that it's just whatever Python can do, that's how it's going to work in Math Inspector, and it's going to add more things on top of that. It's not going to change how Python works. It's only going to take the way that Python works already and then create all of this type of visual interface to really help you, okay? So being able to organize the modules like this, being able to look at the documentation, right? These are all features that Python already comes with. So it's just kind of taking what Python does and then creating this interface, sort of like the difference between DOS and Windows is the way I think about it. What you need to understand is that there's a built-in function called exec. The first argument it takes is a string with Python's source code, and the second argument is the globals, and the third argument is the locals. Let's put this vdict we created A as the second argument for exec and see what happens. So if we do this and then check A, we'll see that the value has been changed to 111. And that's because vdict was made to work with the exec function. Let's actually pull up the built-in exec function from the Add Object menu and just take a quick look at the documentation. So you see here it has the source, and then the globals, and then the locals. And we can view the doc, and it's going to execute the given source code in the context of globals and locals. So what's going on is that when exec updates A in this case, it actually triggered the callback, and that's why it said X here. And so what happens is that the Python interpreter is doing that. Let's take a little bit of a detour and look at this module called code. I want to view the documentation. So it's utilities needed to emulate Python's interactive interpreter. So this is the class that I extended. And then run source, this is going to be the one where exec gets called. And this is what Math Inspector is using. And so maybe the best thing to do is to look at the source code. So we're going to pull up the code module and then, okay, so this is where the magic starts, where it's compiling. It has its own built-in self.compile. And then run code is actually where exec is run. And you can see here it has this self.locals. So it's kind of like built in. So what I did was I made self.locals a vdict, and then exec is going to automatically call the callbacks, which I think is just amazing. I mean, it was really like kind of a lucky break that exec does that. And previously I had written all of the logic myself to do this, where I didn't even know you could pass this these other parameters to exec, and then I threw all that code out and replaced it with basically just a few lines. Let's get back from our detour and maybe come back into the main thing that we were doing here. So we were just going through this file line by line, right? So we had skipped over these lines. This is the node editor. and that's going to be this area. This is the console is here, and then we have the modules, that's this. We're going to now look into this line, the interpreter. In the console folder, the whole console's been broken up into all these different files. So this is the interpreter file. If we come down here, one of the things that's pretty neat is I've actually overwritten the built-in print, help, clear functions, and so on. Just a neat trick. And then this code parsing, this is done with the abstract syntax tree module, AST, and we're going to talk about that a little while later. But just coming down here, we have basically what's going on is each time that you write a line of code, it's going to push it onto the buffer, and that's how it's able to keep track of when you're in a code block or not. And all of this is just leveraging everything that was done in this class that it's extending, Interactive Interpreter. These are the callbacks that we have for self.locals. And so every time that self.locals is changed, let me point out, when interactive interpreter is instantiated, then self.locals is created here. And so now this vdict has actually been instantiated with the self.setItem and self.delItem. SetItem and delItem are right here. And what it's going to say is, if it's a module, you're going to put it in self.app.modules. Otherwise, put it in self.app.objects. So what's really great is that we have the ability to use this same code that we can write in the source code files in the interpreter itself. That kind of symmetry, I just think that's really nice. Each time we're going to push a command, we have to call sync locals, and that's going to update the local store. And then after the command runs, everything's going to be updated automatically. We have the pre-processing step here and the post-processing step here. That is used for connecting the wires together. Just to give an example, if I define a function f, and it's just going to return x plus 1, then if I call f of x, it connected the wires. That's also how it sets the argument when you call, say, f of 15. By the way, we have x and y, so I may as well show you this. If we call f of x plus y, it's created this operator, which is where the whole operator thing came from. I named the operators based on what it's called in the abstract syntax tree class, and that's where I got the list of all the operators. So this type of a thing just makes it really easy once you've written the code for it to like really iterate really fast. So you could just drag your stuff around or come in and type it, and if you start typing, it's going to disconnect the wire. So this node editor, we saw that it was called app.node, so I can, for example, access f, and maybe I want to know what can I do? So if I hit tab, it's got a lot of stuff, right? But it has this function hasArg. So we can see that its argument is plugged in, but if I put none here, it would not work. It would say false. And then the output just changed to function. And so, it's useful. Whenever something changes in one part of the editor, it's going to trigger the callback in app.objects. And then what's going to happen is that's going to kind of cause this chain reaction of all the other callbacks to happen. This file right here is kind of in charge of updating the other views. So in other words, this is in charge of triggering all those callbacks. Again, the big idea here is that we're kind of like anytime one part of the app gets changed, everything has to be synchronized. And so maybe we need to understand, where does the letter V come from in vdict? It stands, like I said before, for virtual dictionary, and the idea is that there's something that's become really popular these days, which is called the virtual DOM. Maybe like React, has a virtual DOM. And so it's a vdict and not a vdom because it's not a data object model, it's just a regular Python dictionary. But the thing is, the idea of a virtual DOM is that once you make a change to the virtual DOM, then it's going to have the callbacks that trigger for all the other views. And so the V here in virtual means callbacks, okay? The whole idea of virtual meaning callbacks. It's kind of weird because it would be better to have called it a callback DOM, but okay. Self.node is, in fact, a vdict. And just to demonstrate that, the node editor, you see it's extending vdict and tkinter canvas. My understanding is that tkinter canvas came first before it even went on the web, and that's where canvas came from. Correct me if I'm wrong in the comments on that, because I'd like to know more if that's true. Oh, well, let's point out that you have to pass self to all of this stuff here. So all of them get instantiated with self, and that's because you want to be able to type self.app in these things. So self.app is going to be set like that. And then, in fact, in here, anytime you type app, that's the same as self.app. Okay, so I'm hoping that maybe these 4 lines are making a little more sense, and then you maybe want to say, well, what's going on here? Okay, really quick, the vertical panel is the one, this is vertical, and this is horizontal. Okay, and then, so what I've done to it is you got to type .add, and then this is the node editor, which is actually inside of a frame because it's got, the reason it's in a frame, it's got this like output thing here. Okay. And so we added then to the console's frame, and so then that makes the node editor go on top and the console go on the bottom. Then we have to call .add again, except now we're doing it for a notebook. Then we're adding the side view and the vertical panel to the horizontal panel, and then using the .pack command to put it into the app. Maybe let's talk about the animation system in a different video, because I would say this constitutes the most technically challenging and complicated part of the whole project. And then we have self.project as save data, so let's just take a look at that. It's in project. It's based on Cloud Pickle, which is sort of like Pickle, except you can Cloud Pickle basically anything. So let's come back to this file. Then what it's doing is it's creating the main menu. So that's going to be this menu right here, okay? And right here it says Python. That's corresponding to the fact that this app is running, but when the app gets built with PyInstaller, it's going to say Math Inspector here. And this line is just configuring the app to use this as going to be the top level menu. And then what it's doing is it's loading your autosave file. Here in the load function, it has this autosave path. Every time Math Inspector is closed, it's going to save the configuration of the app in the autosave.math file. Okay, so there's 2 things that we still need to talk about before wrapping up this video, and that's the plotting features and the documentation system. For the plotting stuff, you can find it in here. Everything in plot is its own self-contained module. It starts in this init file. We're going to talk more about the plotting function in a later video. Let's come back to Math Inspector. If you wanted to perhaps understand the documentation for X, you would type help X, and so that's what happened when I overrode the built-in help function, which is like we saw before in this file right here, where it's going to have overridden the help function. And so then the help function is in doc help. And the thing is that if you come to the main menu, and if you click help user manual, that's going to be the same as just typing help here with the function call. And the idea is that it's really strongly constraining the package structure and creating this very nice connection between the actual package structure inside of the source code files of Math Inspector and how a user who's looking through the user manual is going to interact with the documentation. So if we wanted to understand more about the objects, that's the thing that's app.objects like that. And you see when you click the code, it goes right here. Then it's now, what I'm trying to say is it's got everything that's going on listed here in the documentation on the left. So every time that I'm creating or that we're creating, new sort of extensions of the source code, we have to keep in mind that the package structure and the file structure, it's all got to work together and be one thing. We had this function set object, which that's kind of a big deal. That's what's causing everything to be synchronized when you change the memory, which is stored in the locals. So you see that it's built this really nice document, right? And the way that it did that, let's come into objects. The way that it did that is that it took this thing, which is constructed using the way that the numpy website works, and then it used the tool function doc, which you can actually find. It's in the util in docscrape. I did not write this file. This is part of the numpy stuff for creating their website. You can see that it's also got like a million other things. And then you also have this, this area here where you can go back with your navigation. And that's all being constructed, this navigation system is being constructed from the actual project structure in the source code. Being constrained like that is really important when you are doing anything creative. You know, there's a story about a painter. I heard this from Feynman. You know, and the painter said, well, the way he starts painting is he just draws a line randomly on his paper, because if he's just looking at a blank paper, he's not constrained in the same way that's going to cause the creative process to really blossom. We're really strongly constrained in Math Inspector in the best possible way, and that way is by conforming to the way that Python and NumPy work.